Hello everyone. So before I start, let me thank the organizers for their efforts in organizing this nice event and for the invitation. So I'm very happy to be here. And I will tell you something about dissipative impurity dynamics in one-dimensional quantum liquids. So the big part of this work has been done together with Zoran Ristivojević, who is a CNRS researcher in Toulouse. So I'll start by reminding you about the impurity problem. So you can think about a single distinguishable particle that we are going to refer to an impurity that is coupled to environment, and in our case this will be a many-body environment. Well, this is a fundamental question relevant for a large class of systems, and one can ask very many different questions. For example, the lamp shift can be explained by the interaction of an electron in the hydrogen atom, in that case impurity is an electron, that couples to the quantum electrodynamic vacuum. Also, a lot of efforts were focused on the motion of the helium-3 atoms in the helium-4, and let me mention also one condensed matter setup where one considers the motion of an electron in a crystal, and ions try to screen the electron charge, and as a result, electron gets dressed by a cloud of the phonons, and this is what we call the polaron. Okay, so today polaron is used in more general sense for any mobile impurity that is dressed by a cloud of excitations of the system. However, the resurgent interest in this topic arises due to nice progresses in the field of cold atomic gases, where one can actually, for example, tune atom-atom and atom impurity interaction, not just amplitude but also the sign, using Feshbach resonances, and this will be indeed important in what follows. Then, of course, one can control the dimension of the system, number of impurities, by, for example, mixing different atoms or exciting some atoms in the different hyperfine state locally using laser beams. And I should say that those systems are pure, there are no defects, they are mostly very well isolated from the external sources of decoherence. And of course, there are very nice experimental techniques, high-resolution imaging and spectroscopic methods that can allow to follow the impurity on the atomic size. All right, so all this to say that indeed the cold atomic experiments with the cold atoms opened a new door in the physics of the impurity. In the following, I will be discussing one-dimensional systems, and the natural question is why one dimension at all? Well, we heard very many talks, but anyway, let me just point out that indeed in one dimension, by decreasing the dimension, we do know that the importance of the fluctuations, both thermal and quantum, increases, and as a result, even at zero temperature, there is, if you look at the two-point single particle correlation function, at long distances it decays as a power law, meaning that there is a quasi-longer long-range order, but not long-range order, and this power law exponent k is what we call the Latinger liquid parameter, and it carries information about the interaction in the system. If we have a finite temperature, then there is a new length scale in the problem that is set by the inverse temperature, and this is what I call here small l. And the scale is longer than this thermal length scale, the correlation functions indeed decay exponentially quickly. Okay, so let me say also that, with cold atoms, using the laser beams and the interaction between the atom and the light, one can confine the motion of the atoms in two directions and realize these cigar-like shaped one-dimensional systems. Alright, so we will be discussing interacting bosons, and this is the famous Lieb-Liniger model, where we have indeed two parts. The first part is the kinetic energy, so mass is the mass of the bosons, and the second term is actually the contact interaction between the bosons, the repulsive one. Well, this model is indeed integrable, but in what follows, the phenomenon that we are going to describe is actually absent in the integrable case, so the integrability of this model will not be important for us. However, if we are having weakly interacting bosons, one can introduce this dimensionless parameter gamma. You can think as a dimensionless repulsion between the bosons, where n here is just the mean density of the bosons. So if gamma is weak, a big part of the Hamiltonian can be diagonalized in terms of the Bogoliubov quasi-particles, and here is the dispersion relation. So it's small k vectors. We do have a linear dispersion relation, with v being the sound velocity, and it's given here. However, there is important length scale in the problem. This is the healing length, psi, and if k is bigger than the inverse healing length, this dispersion relation crosses from the linear into quadratic one. In what follows, actually, I must say that residual interactions between the Bogoliubov quasi-particles are indeed important. All right, so I told you about the many-body environment, and we are having also an impurity. So this is the full Hamiltonian. So this is the kinetic energy of the impurity, and it couples locally to the bosons. So capital G is this coupling impurity boson. So what happens actually if you think about the repulsive impurity? This is the density profile of the bosons in the reference system linked to the impurity. So it depletes the boson density locally, and this depletion cloud moves together with impurity. The width of this depletion cloud actually is proportional to the healing length that we discussed, but also depends on the impurity mass and the velocity. In that case, one can actually evaluate the ground state energy of the system as a function of the total momentum measured in units of background, of mean density of the bosons. And this is this curve. Well, the peculiarity of one-dimensional systems is that this curve continues periodically. So if you think about having very small drive, then the impurity will follow this curve, and we are going to have Bloch oscillations even without the lattice, and they were observed experimentally. But what is interesting for me is actually that, so if you think about the derivative of this dispersion relation with respect to the momentum, the critical velocity is the maximal slope of this curve, and if impurity is slow enough, meaning having the velocity smaller than the critical one, then it will flow without dissipation at zero temperature. However, if you have a finite temperature, this hallmark of the superfluidity will disappear, and there is actually a friction force exerted by the bosons on the impurity, and it scales as a t to the 4. Impurity scatters of the thermally excited quasi-particles, and this is the reason why we have this friction force. Well, okay, so this problem has been considered long ago, but by Castronetto and Matthew Fisher, and they have found this scaling. And later on, Langard and Kamenev have determined the prefactor in front of this law. They have expressed it in terms of phenomenological parameters of our system, such as the impurity effective mass, chemical potential of the bosons, chemical potential of the impurity, the parameters that in a general case are unknown. All right, but I should say that those works actually are based on the low energy description of our system on Lattinger liquid theory and its extensions, and that is why they are limited to very low temperatures. Okay, so I will start directly by showing you the final results. So what we have done, we have considered microscopic description of our problem, and using the Bogoliubov-de Gennes formalism, we have evaluated analytically the friction force exerted on the impurity. I'll start by showing you the results for heavy impurity first. So this is our friction force. M is the mass of the bosons, capital M is the mass of the impurity, mu is the chemical potential of the bosons, and P denotes the momentum of the impurity. So we do have a dimensionless friction force that depends on two dimensionless parameters, dimensionless temperature and dimensionless impurity coupling constant G tilde. So what do we see? We have here a rich schematic diagram. Indeed, we do see that at low temperatures we do have this T⁴ scaling, and we have determined the region of its validity. However, if we increase the impurity strength, we find a new interesting region. Actually, this T⁴ region shrinks down, and we have this new T² behavior. And at high temperatures, the force is linear with the temperature, apart from some logarithmic corrections. Actually, this phase diagram depicts the physics behind is actually that reflection amplitude of the Bengaluru quasi-particles scattering of the impurity depends on the momentum and the impurity strength. And here I have plotted its behavior as a function of dimensionless momentum. So we do see that we have three regimes, right? If this is all for very strong impurity coupling, and actually the fact that refraction amplitude becomes 1 is depicted here, and this is this new red region that you see here. I should say actually that the temperature determines what quasi-particles are predominantly excited, and then if you compare with these scales here, you find these crossovers that you see here on the diagram. Well, let me also add that you see that refraction amplitude, actually refraction probability that I plot here at flow momenta is different than 1, and this is actually different. You know that for the free particles in the presence of the barrier, we do have refraction amplitude that is 1 if k goes to 0. Well, we have analytic expressions. For example, if you look how the friction force changes if you go from the yellow to the green region, so this is non-linear function of the impurity strength given here. And in addition, let me say that this region, although the calculations were done for the weakly interacting bosons, we do expect it to appear and to be valid for arbitrary interaction strength. However, in this case, we do not know how this crossover function will look like. All right, so we have discussed the friction force exerted on the heavy impurity, and in that case, one can actually look how the impurity relaxes. The motion of the impurity is stochastic because it scatters off the thermally excited quasi-particles, and one can actually introduce the distribution function that depends on time and on the impurity momentum. One can write down the kinetic equation, and in the case of the heavy impurity, the collision integral simplifies and one obtains the Fokker-Planck equation. This Fokker-Planck equation can be solved exactly, and this is actually the famous Ornstein-Uhlenbeck process in the momentum space. So at the beginning, at the initial moment, impurity has a p-node momentum, and then we find how it relaxes to 0. So this is the mean momentum. It decays exponentially in time, and tau is this relaxation time that is determined by the friction force we have just discussed. If you look at the variance, so it is determined by the temperature, impurity mass, and indeed at short times, short with respect to relaxation time, we do find the diffusive motion in the momentum space with the diffusion coefficient determined by the friction force. And at long times, we do find the Maxwell-Boltzmann distribution. So here I schematically showed how impurity relaxes. All right, till now we have studied mostly heavy impurity. So let me tell you something about impurity of arbitrary mass. In this case, so this is the low temperature result. So we do see this T⁴ scaling. We do have nonlinear dependence on the impurity velocity. But I want you to look at this prefactor here. And we do see that in a special case that is called the Young-Oda model, that is integrable case, when the mass of the impurity equals to the mass of the bosons, and when the repulsion between the bosons equals to the coupling constant of the impurity to the bosons, the friction force indeed vanishes. However, well, this factor also becomes 0 under less restrictive condition. And in that case, one has to consider higher order terms, and we have dramatic change of the friction force that scales in that case as the 8th power of the temperature. I should actually point out that although this result is a low temperature result, the nonlinear dispersion relation of the Bengaluru quasi-particles is crucial, and that is why the theory is based on Latinger liquid theory, and its extensions cannot describe it. All right, so we have discussed weakly interacting bosons till now, so let me now tell you something about the same question, but in the case of strongly interacting bosons. In that case, our parameter gamma is much bigger than 1, and actually Patricia yesterday explained us that in the case of the Tongs-Girardot model, when gamma is infinitely strong, she explained us how to map Tongs-Girardot bosons to the non-interacting fermions. But we can also consider gamma that is not infinitely strong, and in that case we do have a mapping, but this time we do have interaction, and attractive one, between the fermions, and this is what is called as a Chernow-Shigehara model. If we evaluate the friction force exerted on the impurity by the fermions, it will be the same as the friction force exerted by the bosons. So in this case, the leading contribution comes from the scattering of the impurity of 2 fermions. So this is the initial configuration. We have initial momentum of the impurity P, and P1 and P2 denote the momenta of the fermions. And this is the outgoing configuration. We have a momentum Q, and Q1 and Q2 are outgoing fermions. Well, in that case, if we are at low temperatures, the conservation of energy and the momentum tell us that fermions have to be around the Fermi points, and there are several processes. Either they are around different Fermi points, or they are around the same Fermi point. This is what I refer to as 1-1 or 0-2-2-0 processes. And okay, we have a full analytic expression, but what happens actually is that this process gives the leading contribution, and this is T to the 4 scaling, and these 2 scales as T to the 10th power of the temperature. All right, but if we can control the interaction strength between the bosons, in that case, if we have a critical repulsion that I have written here, in the case of the impurity mass being different than the mass of the bosons, this friction force vanishes, and we have dramatic change. We find that the friction force in that case behaves actually as the 6th power of the temperature. All right, so with that, okay, it's time for conclusions. I have discussed the friction force exerted on the impurity in the case of interacting bosons in 1 dimension. We have found a rich schematic phase diagram. What next? Well, it would be interesting to see whether using the impurities one can create quantum probes such that in non-destructive way we can extract some information about the system. For example, this what I have shown you. Can we use this impurity as a quantum thermometer to measure the temperature of the system? Then, there is a very nice question about the bipolar formation. Well, if you have, for example, 2 impurities that interact with the system of the bosons will mediate the interaction between those 2 impurities. In some cases, it is attractive one, and one can have a quantum mechanical bound state of the impurities that goes under the name of the bipolar, and it would be nice to understand how it forms. Of course, driven impurity is also an interesting topic, and all these results indeed call for more detailed analysis of the same question, but in higher dimensions. Okay, with that I finish. Thank you very much.
Long live India and France friendship.